And how did you deal with the phase anomalies that crossovers introduce, in this thing? I mean, do you phase align are your crossovers all phase aligned so that, you don't run into time problems at the speaker end?
So phase and group delay. Group delay is even worse than the phase. Group delay is the second derivative of the response. So horns is a bit different than direct writing in drivers because they have phase, let's say they have group delay built in to the horn. So they have alternating response on both ends, low and the high pass and low pass. So you have to work around that one. So you don't see the crossover as a crossover plus a driver. You have to work around the impedance of the horn of the driver, which is altered by the horn itself. Okay, you also have to work around the impedance to shape your crossover in order that the passband group delay and the stop band is as linear as possible. And then you time align them. Because if you time align, let's say two drivers, two horns, right? They're going to be time aligned at a very, very narrow frequency range. They're not going to be aligned for all their passband and in their stop band. So what you are trying to do is you maximize the alignment of these two ways by using by linearizing the group delay of the two, and then physically aligning them. And to go another step further, you don't just physically aligning something doesn't mean they are aligned, because sometimes the acoustic center is either more to the back or to the front. Usually the ribbon drivers, okay, their acoustic center is much behind the drive. So compression driver, its acoustic center is you have to find it. You have to measure where it is, especially in combination with the horn. So it's not a matter of, okay, get the voice coils together, and call it a day. It's no acoustic driver, acoustic center will change depending on frequency in combination with your group delay that is introduced from your filter. So you have to design everything in unison to get something that will sound, remotely coherent, which is very difficult to do with horns. The problem with big horns is that you align them in a specific axis, a specific listening axis. So they're a bit selfish kind of speakers. They sound incredibly good at a certain position, but if you are, let's say, offset, they're not going to sound the same as, let's say, a very, very wide radiating, direct radiating speakers. They behave very, very differently in a room. But you can't have it all. And if you're being cynical about it, who pays for it has the best spot. So
the money seat, as we always say.
I loved your example of calling it a selfish speaker. It's a fantastic way of putting it.
Yes, I pay for it. It sounds good in my spot. I don't care about,
I don't care who's sitting next to me. Who's the wife?
Something like that. I don't care if it sounds good in the kitchen. I don't care.
So, I come from a little pro background as well. And when we set up pro systems, time alignment, as we talk about, and this time alignment, but time alignment is true only for one seat in the house, right? I mean, it's going to vary because of the part differences that vary across multiple seats. So how do you then get a wide enough sweet spot? Or these speakers don't give a wide. Being horns, I thought they'd really give like a really wide sweet spot, or they just don't. They're very selfish, like you said, and they are a point listening place only, like bang in the middle.
It's physically impossible when you have drivers which have different positions in space, that is horns or panels or whatever. If you have drivers which are different locations in space, you cannot align them in more than one axis. They're going to be aligned in a specific acoustic axis, and that is it. Doesn't matter if it's horn or it's just normal drivers or big panels. That doesn't matter. If they are positioned, if they are not overlapping in the same position, they're going to have a specific axis which they sound great. That's why in Pro Audio it doesn't make sense to be time aligned. Time aligned where? For who? In home audio, it makes sense because usually the guy who pays for it, is in a
The
sweet
money
spot.
seat you're talking about.
Exactly. In Pro, you're gonna get them close enough, right? Let's say you have an
It's
array
compromise.
forward, yeah, and let's say you have the bass much to the back or to the front, then you're gonna have some time alignment, but not to the accuracy that you can get in a home environment, which are talking about accuracy of millimeter. This is the level of accuracy you can get with the tweeter and a mid-range. Difference of a millimeter is detrimental to getting that. It doesn't make any sense, or it doesn't. Let's say it's not possible, and again, it doesn't make sense for Pro Audio. You get only within a few meters, let's say, because you have a big stage, you have the RS in the front, the bass is, let's say, 10 meters behind you. Of course, you're going to get it closer, but we're not talking about the same ballpark here about actual time alignment. We're talking about millimeters there. Yeah. Same thing with the bass. A lot of people were asking us about the bass horns, why they were much forward than the main speaker.
Yeah, in Munich, it was right up front there.
Yes. So the answer is, that's the only position they are time aligned. If you push them back, they will look better. They will look conventional like most bass horns. But if you, let's say, unfold the 4.5 meter bass horn, if it's in the back, it's going to end up another 4.5 meter
behind
the back, right? They're never going to be time aligned. If you push them forward and that position will have them. If you unfold it, you'll see that the drivers will
sitting
go
way behind. Yeah,
they will go and coincide with the mid bass drivers of the big mid bass. Going to be in the same, let's say, virtual position. That's why we're aligned in the bass, especially when if you are near the bass, you cannot hear the bass coming from the bass horn. You hear the bass coming behind the mid bass. That's how you can tell they are actually aligned. But it doesn't, let's say, it doesn't look conventional to have that huge bass horn in front of it. But the only way to do it, if you don't want to go on DSP.
I noticed that your bass horn has got 8 drivers, right? I mean, you've got six. So, and I also read that these drivers you get manufactured from a manufacturer who's got expertise in bass driver manufacturing. So when you put 6 drivers together in a horn, don't they have to be matched like really, really closely? Because, even if, say, like someone's suspension is a little tighter than the other, it's going to like completely be at odds against the other drivers which are trying to work in unison.
On the chamber on the chamber design. So it's for example, how you divide them in the chamber and how the pressure is handled. So it's you can load a chamber with different drivers with some tricks. So if you can do that, imagine that the variables between the drivers is not affected, especially the bass. Where it's very important is on the upper mid range. On the upper mid range, it's much more important, and the geometry between how you combine the 2 compression drivers, that's very, very important. The lower you go in frequency, the more the wavelengths goes so high that the variations in the chamber are non-significant, actually zero significant.
And you're talking about chambers and talking about compression drivers and compression loading and stuff, and then you go and design something like the Aurora, which is an infinite baffle design, which is folded in on itself, kind of. So you want to talk a little bit about how that came about? I mean, after working with all these kind of designs.
The Aurora was let's say, started as an experiment and say, okay, the best base solution for me, at least for myself, is bass horn, period. You cannot surpass that base
Better than
technology. So what's next? What's the second best? I really hate bass reflex. This, once you hear the defects, you never go past that. Closed seal box is very nice, especially in infinite baffle variations when you have very, very high Qs, for example.
and then you don't go that low.
No, you can't go. Depending on driver, you can go down 10 hertz with infinite baffles. But the sound is very closed. What I like. Open baffle sound have this a nice sound to it. They never have the impact, and then they can never go low. So I said, okay, how long we can push this tech to go, to go near, not near bass horns, because they have very, very different delivery and very, very different, let's say, wave formation characteristics, very, very different. So how good can we make this one? So, open baffle, you have to have very, very large baffles to have some lows, 4 or 5 meter baffles. So what I want to do is having a baffle which will fold on itself and create back pressure. So the exit of let's say the combined pressure, let's say, from the 4 drivers, the exit will be, how to call it, choked. Okay, so let's say the surface and the surface that generates sound from the front will be always higher than the back. Will always create some back wave. So that's where you get more dynamics, you get more extension. It had some issues because whenever you have some cavity, you have to overcome resonances. So we have some nice tricks there with the configuration. Also, you get some other, let's say, side effects, nice side effects, because you have much more nicely and uniform loading of the room because you have 4 sources. So the modes and peaks and dips will even out, which was a nice side effect of that loading. An Aurora, even though it could deliver much, let's say, bass pressure, a lot of energy in the room, it will very rarely boom and have this
Boomy
boom
side effects, artifacts.
And this is because of the let's say the 4 directions lowering and the phase of the back wave, which creates some very, very interesting patterns, characteristics.
And be very fast also, so you'll get brilliant attack then, because there's no back resonant mass pushing back on the driver.
Especially if you use very light drivers, which we like to use. Open baffle usually use very, very heavy drivers. Very heavy to have low resonance to get some, usable bass. But we went the opposite. We use very, very light drivers with no foam suspensions, with let's say, with accordion closed suspension. So very, very fast drivers. So it allowed us to operate them at much higher frequencies and across them much higher, which is also a nice characteristic of the Aurora. It doesn't have just the open baffle just for the bass, and then you have a gap between the bass and the horn. You still have this very, very nice speed crossover to the large mid-range.
And even the swirl baffle on the mid-range is something very interesting that you've created in the Aurora. That was to address another problem, right, that you had.
Yes. So what we always do, horns, we always do the rollback. The rollback is always there for the diffraction. But let's say you have the mid-range and then you have a cube. So you can't do a rollback. So it's impossible. And then I sat down and figured out, and we tried to design something and see how can you transition from a mouth of a horn to a cube, which is sitting, a feet behind it, and having no diffraction. Diffraction is always created when you have abrupt geometry. So when you have abrupt geometry, especially we have patterns. Let's say you have equal distance between surfaces. You have corners. So what we try to do is having this swirl shape, which if you analyze it, the traffic curve at 0 degrees, it splits into 4 sections, and then it rolls back. And the geometry is always, it's never abrupt changing. So the second derivative is always, continuous. But it's very, very smoothly transitioning to the cube. So by doing that, with the diffraction is not the same level as a full 360 degree, which is impossible, but it's very, very difficult to measure. So if it's difficult to measure, then it's probably inaudible. So I think that's the second best thing to a 360 diffractionless horn.
One last question I have before Karthik can take over and the same. What is your view on cylindrical wavefronts as compared to spherical wavefronts? I mean, when I talk cylindrical wavefronts, obviously I'm talking about line array theory, and a lot of home manufacturers seem to be encompassing or incorporating this in there by coupling multiple tiny drivers together in order to try and take advantage of the line array effect and create that cylindrical wavefront, so that you kind of widen the sweet spot and every seat gets an even SPL response.
The sweet spot, you don't widen it, because the line array is going to be only for the ceiling and floor diffraction. Is not going to do anything. It's not going to determine your polar response on the horizontal axis. So it's not a matter of wide.
But you will go very wide in the horizontal space. When you stack speakers on top of each other, the horizontal dispersion increases dramatically.
No, this depends on other factors as well. It doesn't matter that a line array will always be wide dispersion. A line array horn will still have a horn characteristic on this horizontal axis. So line arrays are very interesting, and we also do some experiments. For example, we try to see how long we could do the ribbon horn driver. And I always find, and this is what I always find striking in big panels, I find that especially on upper, mid, and high frequencies, there is a very, very bad effect once you get more than 20 centimeters or so in length. So the problem is that, let's say you have a 2-meter long ribbon. The cylindrical wave is pretty much theoretical, right? The problem is that the source on the bottom and the top is not going to align with the front one. The ear will pick it up. It doesn't behave the way you think it will behave. It's not a ruler coming, a big cylinder coming at you. And a very, very striking way to listen to is put some string material, let's say guitar, acoustic guitar, or even a piano. Once you hear a big ribbon, 2-meter ribbon, and you hear these characteristics, you can't hear it. And a lot of people that I'm discussing with, which love panels, once they hear this effect, they don't realize what it is until they get to understand the physics of the ribbon. And then the problem is you cannot hear it, and a lot of people are moving away from a lot of panels. If that panel had small ribbon, it will solve a lot of its issues. So we also experiment with very, very long ribbons, horn-loaded ribbons. You get other things. Let's say you get more pressure, you get more, let's say, punch. But I find the limit, if you go over 20-something centimeters, you always get this effect, which it's for a user is difficult to pinpoint what it is, but it's very, very audible, especially on very, very transient, like single string or not a cymbal, not a, but a very, very distinct string. It's very, very audible.
Or a piano.
If you compare a big ribbon with the with
No,
the,
when you talk about a large ribbon, you're talking one single ribbon that long or 2 meter long, or you're talking about multiple, like say maybe 10 centimeter ribbons which are
even
put
if you have
together.
multiple, the problem is how close you can get them.
Correct.
All right.
That's
If
always
you,
been the
if
line
you
array
have
problem.
multiple and you get them close enough, they can, let's say, simulate a big ribbon.
As what you're saying.
So the problem is line arrays, but for which frequency? So it's not, let's say,
The line has to be the height of the frequency it's trying to reproduce, right?
I think let's say subjectively speaking, even though it's not, it's objectively speaking, because you can measure that effect. The higher the frequency, the less you want to move from line arrays. At least in my opinion.